Now let's look at the W algorithm itself, because we have all the groundwork now. We have substitutions, we have unification. When we carry out the algorithm, we give it an expression E, and we give it a type environment that assigns types to all the free variables in E. So the algorithm is W applied to type environment and an expression E. We're also going to assume that out there we have a constant type environment, sigma, that assigns a type to every constant in our language. In our case, it's really quite straightforward, namely that the type of the constants true and false are bool, and the type of 0 is int, and the successor function is a function int to int. So when we call the W algorithm, what do we get? Well, either we get a type, which is what we want, and a type substitution that tells us the type for each type variable, or we get fail, in which case we know that our expression E cannot be typed. As I said before, the W algorithm will try to build a type derivation. So in the algorithm, there is a case for each type rule. And now I'm going to explain the W algorithm. And in it, I'm going to refer to the type rules directly so that we can see what's going on. First, let's look at the case of the W algorithm where we called it with a constant. When we call the W algorithm with the type environment and a constant, it's really quite simple. To infer a type for the constant, we simply look up the type of the constant in the type environment. We simply return the type sigma of C, and the substitution is just the identity substitution. There's nothing to say. Now, if we're looking at a variable, the type rule for variables is the one that we're simulating with the algorithm. The type rule for variables says that if the type environment says that x has type t, then we conclude that x has type t. So in this case, if the expression we're calling the W algorithm with is x, if x is found in E, and the type of E is some type scheme here, and these are new type variables, then we return the identity substitution and S. If X is not found in the domain of the type environment, then we fail because we are talking about a type variable that was not mentioned. Now, how do we handle function abstraction? Well, the type rule for function abstraction said that if we have a lambda x dot e, then this should have an arrow type t1 to t2. And that's the case if the body E has type 2 in an environment that's extended with the assumption that X has type T1. This is captured by the following clause in the algorithm. It says that if we are trying to find the type of a lambda expression, then we introduce a new type variable A. And we add the assumption that X has type A to E, and then we try to find the type for the body E1. And if we get sigma and T out of that, then the substitution is sigma, and the type of the function is whatever the type is of the argument, that's sigma of A, to T, because T was the type of the body. Now, application is where unification comes into play. The type rule for typing an application says that E1 applied to E2 has type T2 if E1 has function type T1 to T2 and E2 has the appropriate type, namely T1. So that's the type rule. The clause in the type inference algorithm says, okay, we're supposed to find a type for E1 applied to E2. So we try to find a type for E1 and a corresponding substitution. So we find sigma 1 and T1. And then we try to find a type for E2. And we do that using the substitution that we have. We apply the substitution to E such that we know what the type variables in E stand for. And then out of that, we get a new substitution, sigma 2, and we get a type T2. And then we introduce a new type variable, A, which stands for the result type of E1, the function E1. If both of these recursive calls succeeded, then we try to unify T1, or rather sigma 2 applied to T1 and T2 to A. We're trying to find out if this is if we can find A. And if we can do that, then the type is sigma of A. And the substitution that we get is, well, it's not sigma 1, but it's sigma 2 composed with sigma 1. First we know sigma 1, then we extend that information with what we know in sigma 2, and then finally we get some more information about the types from sigma, so it's sigma composed with sigma 2 and sigma 1. If one or more of these calls will not succeed, if we cannot unify, or if one of the sub-expressions E1 or E2 cannot be typed, then we fail. Now the type rule for pairs is similar to the previous case, only simpler. The type of a pair E1, E2 is T1 times T2 if E1 has type T1 and E2 has type T2, all in the same environment E. So when we want to find the type of a pair, what do? Well, first we try to find the type of E1 using the W algorithm. We get a type T1 and a substitution sigma 1, and given that we now know sigma 1, we apply sigma 1 to E, and we then try to find the type of E2, and we get the type T2 out of that and a new substitution sigma 2. So the type of the expression is T1 times T2, and the substitution is the composition of sigma 2 and sigma 1. Think of the substitution as talking about what we know about the types. So first we know sigma 1, and afterwards we know even more. So this is sigma 2 composed with sigma 1. Now the Hindley-Milner-Damas type system is a polymorphic type system, and in this particular rule, polymorphism becomes very visible. If we want to check that a let expression has type T, what must we do? Well, firstly, we must find the type of the local definition E1. If E1 has type S, then we can type E2 under the assumption that X has the closure of the type of S, meaning that we introduce quantifiers for every free type variable in S. So this is where we add universal quantification. So in the type inference algorithm, when we're trying to find the type of the let expression E, let X be E1 and E2, first we try to find the type of E1, and suppose we get a type S1 and a substitution sigma 1, then we must find the type of E2, but we do that in a type environment E prime, which is the one where we have applied the knowledge that we have from sigma 1 to E, and then we add an assumption that X has the type S1 with quantifiers added. This is where the close comes in. If all of these calls, or both of these calls, work out fine, then we return S2, and we compose the substitutions, because first we knew sigma 1, and then afterwards we knew even more, so this is sigma 2 composed with sigma 1. If one or both of the calls failed, then the algorithm fails. So these were all the cases of the W algorithm. Now the W algorithm that we've just seen is a very nice algorithm. It's sounding complete. By sound I mean that if the algorithm, given a type environment and an expression, produces a type and a substitution sigma, then whenever we know that E has some type T1 from the type rules, then that T1 is an instance of T. T is, in other words, the most general type. We also say that T is the principal type of E. Now, completeness means that if we know that E has some type T1, then the W algorithm will produce a T such that T1 is an instance of T. So whenever an expression is typable, we will find its type, or rather we will find a type that is more general than it. So these are very nice results about the algorithm, and these are the results that make the algorithm useful. But is it a fast algorithm? Well, it was discovered in 1977, and for almost 10 years everyone thought that it was a very nice algorithm in the sense that it had low polynomial time complexity, because in practice the programs that we encounter have small types that are easily found. But it is a slow algorithm in some cases. The W algorithm has exponential time complexity, and the type inference decision problem, which is given an expression E and the type environment E, can we find a T such that E has type T in E? That problem is even exponential time complete, so it is the worst of all exponential time problems. And this was in fact shown in 1989 by Kfouri, Churin, and Rosichin, and independently of them by Merson. And what we know now is that some expressions have principal types that are huge. Here's a program that's adapted from an example due to Michael Schwarzbach. It's a Haskell program that has an auxiliary function pair that takes an argument z, and then returns z applied to xy, and then we have w, which is x4, applied to the identity function, where we have x4 defined, x3, x2, x1. We need not know exactly what this program does, but what we do know is that if we try to find the type using the Haskell system, we will get a type, but it is huge. And why don't you, when you can find the type, try asking Haskell to find the type? Now, another question one might ask is, why stick to Hindley, Milner-Damas? Because we know that there are type systems that have richer notions of parametric polymorphism. In the Hindley, Milner-Damas type system, all the type schemes have all the quantifiers at the leftmost end. So they're written as for all A1 ... for all AK T, where T is a type with no quantifiers. Wouldn't it be nice if we could put quantifiers wherever we please? And indeed, we can do that. And one example of such a type system is the second-order polymorphic lambda calculus that's due to Girard and Reynolds. And for quite some time, people thought, well, maybe we can do type inference in that system as well, because if we could do that, then we would have that as our type system for Haskell and not the Hindley, Milner-Damas type system. Unfortunately, Joe Wells showed in 1999 that typability and type checking are equivalent problems. If we could solve one, we could solve the other, and in fact, they're both undecidable. So the Hindley, Milner-Damas type system is probably as far as we can get, while still being nice. Even if we extend it very slightly, we run into problems with type inference. So this is probably as far as we can get within the world of parametric polymorphism. Now, of course, we've only covered parametric polymorphism. In Haskell, there's ad hoc polymorphism as well. We've got type classes. It turns out that even with type classes, type inference is still possible, and this is a fact that we know from results by Wadler and others in the 1990s. I'm not going to go into it here, but with the addition of type classes, nothing goes awry, and that's at least nice to know.